Welcome. In this lesson, we're going to talk about Newton's second law and how it applies to motion of systems of mass, extended objects. And we've really already been doing this. When we've been drawing free body diagrams, we've been drawing the forces acting on the center of mass of the system. So, I mean, really, this is nothing new. And when we think about extended systems of mass, Newton's second law still applies. So we can be explicit about this. The sum of all of the external forces acting on the system. And again, when we were talking about objects like cars and Atwood machines and things like that, we ignored internal forces when we talked about the acceleration of the system. So the sum of all the forces, the external forces acting on the system, is equal to the total mass of the system times the acceleration of just the center of mass. All right, so throwing a hammer in the air, a baton in the air, things like that, we're just concerned with the center of mass. So let me show you an example of why we've already been doing this. If we talk about a car that is accelerating down the road, yes, I know it's a nice car. Really, when we draw the forces that are acting at the point of contact, we've got a normal force going up here on this wheel, a normal force going up here on this wheel. We've got a force of static friction here going that way, another force of static friction here going this way. We have the weight of the car, which is going down from here. So all of these different forces are acting on different parts, different little discrete mass units on the car. But when we talk about the acceleration of the car, we're really just talking about the acceleration of the center of mass. And when we talk about all of these external forces acting on the car, we're ignoring internal forces. Because like the tires are pushing up on the axles, which are pushing up on the car, and all sorts of these internal forces we totally ignore. So we have already been doing this. The external forces, the sum of the external forces acting on the object is equal to the total mass of the system, in this case the total mass of the car, times the car's acceleration, or the center of mass of the car's center of mass's acceleration. All right, so let's apply this specifically to a couple of different situations. First, we're going to look at throwing a hammer up in the air. All right, so here's our example. We've got a guy holding a hammer. I know I'm an amazing artist, and here he is. Mass of the hammer is 1.5 kilograms, and this guy wants to throw the hammer up in the air, maybe toss it to his friend who's standing over here. So the hammer is going to follow a parabolic trajectory, and really it's just the center of mass of the hammer that's following that parabolic trajectory. So the center of mass of the hammer is like right there. Okay, and regardless of where this guy is holding the hammer or throwing the hammer from, the hammer is going to go end over end as it goes to his friend. But the center of mass is just going to follow that nice parabolic trajectory, just like it was a ball or something like that. Okay? So what we can say here is that, let's say the center of mass of the hammer goes 30 centimeters with the guy throwing it. From wherever the guy starts accelerating the hammer to the instant he lets it go is 30 centimeters. And let's say he gives the center of mass of the hammer an initial velocity equal to 8 meters per second. The question that we can ask is, what's the net force acting on the hammer as this guy's throwing it? The next question we could ask is, what is the upward force on the hammer's center of mass? Okay? So we don't really care where the center of mass is here. We don't care where the guy is applying the force. We just say the sum of the external forces acting on the hammer is equal to the mass of the hammer times the acceleration of the center of mass of the hammer. All right, so free body diagram on the hammer. We've got the hammer's weight going down, mg, and oh gosh, I don't know. Do we want this guy throwing it diagonally? No, let's just say he throws it straight up. Forget the whole parabolic trajectory thing. He's going to throw the hammer end over end straight up and catch it. All right, so he's got some upward force that he's applying to the center of mass of the hammer. Okay, so that those external forces are the upward force minus the weight of the hammer. That's equal to the mass of the hammer times the acceleration of the center of mass of the hammer. All right, so really, when we're asking for this first question here, the net force acting on the hammer's center of mass, that's this side, the left side of our equation. So we just need to take the mass of the hammer times the acceleration of the center of mass of the hammer. So we've got to do a kinematic equation here to find out what that is. So our change in velocity is equal to 8 meters per second. And our delta y here is going to be 0.3 meters. So we can use v final is equal to v naught plus 2a delta y. V final squared equals v naught squared plus 2a delta y. We're solving here for a, so we get v final squared minus v naught squared divided by 2 delta y is equal to a. So plugging in numbers here, we've got 8 squared divided by 2 times 0.3 is equal to the acceleration of the center of mass of the hammer. Plugging that into the calculator, I got 106.7 meters per second squared for the acceleration. That's quite a large acceleration. So 106.7 meters per second squared is a, so plugging that in here, F net is equal to the mass of the hammer, 1.5 kilograms, times 106.7 meters per second squared. And putting that into the calculator, we end up with 160 newtons, which is not a huge force, so seems kind of reasonable. So that answers the first part, and then we're going to take that 160 newtons, and that's going to go back into our equation up here for the net force, and we're going to look at these guys. F up minus mg is going to equal 160. Plug those in and solve for the force that this guy really applies in the upward direction. All right, this is 160 newtons the net force. So the guy actually doesn't have to apply that much force. It's going to be that minus the weight of the hammer. And the weight of the hammer is 9.8 times 1.5. So we end up with about 145 newtons of force the guy only has to apply upwards to get the hammer going. So this problem really is no different from any other problem we've been doing. All right, next example, let's take a look at one that's a little bit more complicated, with a person on a raft walking from one side to the other. Okay, so this is a pretty classic physics problem here. A person standing on one end of a barge, and they walk from one side to another. Here we're going to ignore water drag, but we see other kinds of problems. Two guys sitting in a canoe, different masses, they exchange places. Where does the canoe end up? So what we're going to ask is, this person is going to walk from the far left side of the barge to this position here, which is going to be 0.5 meters from the right-hand side. So first question is, what is the change in the x position of the center of mass of the barge? And the center of mass of the barge is someplace. The center of mass, of the barge is here. The center of mass of the person, at least the x-coordinate of the center of mass of the person, is here. So the center of mass of the barge person system is going to be someplace just to the left of the center of mass of the barge. Okay? And when the person walks from the left side over there, what we can say is the center of mass of the barge person system doesn't change. If there are no external forces, then the sum of the external forces has to be 0, because there aren't any external forces acting on this system since we're ignoring water drag. The weight of the barge person system and the normal force cancel each other out. So this is 0 meters. The center of mass of the system doesn't move. However, the person does move, and the barge itself does move. So the next question we ask is, how far does the barge move? As a result of the person's movement. If the person moves to the right, the barge is going to have to move to the left. And this is the key factor right here. The center of mass of the system doesn't change. So first we've got to find the center of the mass of the system. So it's the total mass of the system times the center of mass is equal to, and we're only considering the x coordinate of the center of mass. It's not actually right here where I drew the purple dot because it's going to be some distance above that if we consider the y coordinates. But let's just ignore the y coordinates because this question doesn't deal with any vertical. So we're just considering x, so it's going to be the mass of the person times the person's position plus the mass of the barge times the barge's position of the center of mass. Let's say x, let's just say, I don't want to do that. Erase, 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 erase. Mass of the barge times the center of mass of the barge, because that's really what we're concerned with here, and this is the x coordinate. Okay, so to find the center of mass system, total mass, let's see, mass of the person I've drawn over here on the left is 70 kilograms, mass of the barge is 200 kilograms, so we've got a total mass of 270 times the center of mass of the system. Let's say our origin is over here, 0, 0 on the left-hand side of the barge. So the mass of the person is 70 and his position is 0 plus the mass of the barge, which is 200, times the position of its center of mass. We use symmetry. The center of mass of the barge is halfway, or half the distance of the barge, so it's 1.5 meters, since the barge is 3 meters long. So solving for the center of mass of the system, we've got 200 times 1.5 is 300 divided by 270. And throwing that into the calculator, we're going to get a center of mass of 1.11 meters. So this little purple dot right here, before the person moves and after the person moves, is 1.11 meters from the left-hand side of the barge. All right? So if that's the center of mass of the system, what we know, again, from the first part of this problem is that center of mass doesn't change. All right? So now let's talk about after the person moves. We again know that the total mass of the system times the center of mass of the system is equal to the mass of the person times their position plus the mass of the barge times its center of mass. So here we know XCM, it's 1.11. Total mass of the system is still 270. And the mass of the person is still 70 kilograms. They are now 2.5 meters to the right of the origin. And we're looking for, whoops, sorry, we know the mass of the barge is 200. And we're looking for where that center of mass of the barge now is. It's not going to be at 1.5 anymore. It's going to be someplace to the left. So we do our algebra, and we find that the center of mass of the barge is now at 0.625. meters to the right of the origin. And remember, it started at 1.5 before the person walked. So started at 1.5. It's now at 0.625. So if we subtract those, we see how far the barge moved to the left. I think I said right earlier. How far it moved to the left, and we end up with 0.875. So it moved 0.875 meters to the left. That's it. We are going to get into more of these center of mass problems when we talk about momentum. But for now, your homework is going to be Chapter 5 problems numbers 115 and 137. You need to do those tonight for homework, and we're going to be talking about them in class next time. See ya.